One of the really beautiful aspects of the theory of species of structures is that it lends itself to very intuitive visual proofs. And in order to understand these visual proofs, it's necessary to develop a vocabulary of visualization. So let me just introduce the basic ways that we have to visualize species. I mean, this is not a mathematically rigorous lecture, but more of I'm trying to explain to you how you should think about things. So usually the set U, finite set, is denoted by a sequence of dots. So is depicted by a set of points. It's a finite set, so we would visualize it just as a bunch of points. And one way to put an F structure on this, the visualization, is to draw it like this. So these dots are the points of view. Maybe I should write here. These are the points of view. And when we put an F structure, we depict it like this. So we may put this whole thing inside a box. So this is one way of denoting an F structure on U. We draw this sort of rays going into the set U and write F across them to say that, okay, we had this set U and now we have imposed an F structure on it. So this is an abstract species one visualization. And another commonly used visualization is to just put all the points in a box. And then write F in the box. So that means that now this set of points has acquired an F structure. So these are sort of general abstract visualizations. But for specific species, there are very natural pictures that we might wish to draw. So for example, how would we draw a picture of a permutation? So what is a permutation? Well, we have a bunch of points and we have some directed graph which takes each point to some other point, and it just, it's every node has one input, one in arrow, in edge, and one out edge. So we may visualize, when we want to visualize the species of permutations, we would draw a picture like this. And in the last lecture, we saw a species called inv0 of U, which means fixed point free involutions. We would visualize that as something like this. Whereas we may visualize perfect matchings on the complete graph, the species that I called M2 in the last lecture, in the following manner. Let's just make these dots a little bigger, and this is the species M2U. And it's evident how from this picture it's clear that you go from this kind of picture to this picture, you replace every pair of arrows by an edge. And so this is a proof without words that inv0 is equal to M2. So just by looking at this picture, you will be able to understand that the species inv0 is isomorphic to the species M2. Let me give you a few more examples of visualizations. The species of set partitions, par U. So you would draw the set U as usual as a bunch of points, and then you want to indicate that you have partitioned this set into pieces, and so you would just draw maybe some subdivisions inside this set. So this is an example, this is a visualization of the species par U. You can look at the species of cycles on U, cyc U, and here you would just you don't have to draw the most general picture, but just a picture that conveys the essence of the species. So for cyc U, you might draw a picture like this. This, of course, is an art in the sense that how you draw the species and the pictures would depend on what you want to prove. But this is, once you look at this picture, it's clear to you what a cycle structure on the set U is. And so let me just introduce a new species using a picture, and let's see if you can understand just from the picture what it is. So I want to introduce a species just by drawing a picture, and I'll call it lin U. And what it is I have a bunch of points, and I just have okay, so what does this picture suggest? So this picture suggests that you put the structure of a line graph on U. We also have the species of linear orders on U, which I called LU, and this is just slightly different in the sense you specify which side of this line is the minimum and which side is the maximum. So you must draw arrows. And if you look at this lin U, you can ask what is the cardinality of lin U. We know that the cardinality of LU is n factorial. So for lin U, well, for each linear order, there are two possible line graph structures, one going from the maximum to the, for each line graph structure, there are two possible linear orders, depending on whether the left edge or the left end or the right end is the maximum. And so lin U is going to be, the cardinality of lin U is going to be the cardinality of LU divided by 2. Well, of course, if cardinality of U is greater than, greater than 1, that is if it's at least 2, and it is equal to LU for U empty set and set with one element. So that's some examples. Let me give you a more amusing example. So we'll encounter this example later again when we study. This is called the species of octopus structures on U. So the picture looks something like this. So an octopus structure on U means that you take some points of U and you form a cycle, but then you have more points on U which are somehow connected to that cycle. So this is an example of an octopus structure on U. For good measure, as traditional, I'll enclose it inside a box. And what would you formally define an octopus structure on U? It is a simple graph structure on U. It should be connected. Directed graph structure on U. It doesn't matter. We have not given arrows to these legs of the octopus, so to speak, but each leg has an obvious orientation. You move from the tip of the leg towards the body of the octopus. So whether you draw these arrows or not, it doesn't really convey any extra information. So we can think of this octopus as a simple connected simple direct graph structure on U, such that we have with the central cycle which is the body of the octopus. Maybe I'll call it U1, U2, UK to U1, and a series of legs. VI1, VI2, VIRI, and then it joins the body somewhere, let's say at UI, for each I, for some Ri greater than or equal to 0. And the sets U1, UK, VI1, VIRI, I goes from 1 to K, are all pairwise disjoint. With union U, every point is involved in this octopus. Transport of structure in all these cases is kind of obvious once you define it. Once you define what an F structure is, it's obvious what a transport of F structure should be. So I won't describe that.